At this point in chemistry, you've at least read some text that talks about something called a mole. Well, we obviously know that a mole is an animal, but in chemistry it means something much different. So what is that? Well, it's simple. A mole is just a counting unit, like a dozen, or a pair, or a gross. Now, one mole is always equal to one certain number, just like a dozen is always equal to 12. Well, for us, the number you need to get ingrained in your mind is that 1 mole is always equal to this number, 6.02 times 10 to the 23rd of whatever you're talking about. And another name for this number here is called Avogadro's number. And that's because the guy who came up with it, his name was Amadeo Avogadro. So just like a dozen, a mole is always equal to 6.02 times 10 to the 23rd, no matter what you're talking about. So a mole of dollars, which would be awesome to have, is 6.02 times 10 to the 23rd dollars. A mole of chemistry tests, which would be awful, is 6.02 times 10 to the 23rd chemistry tests. A mole of houses is 6.02 times 10 to the 23rd houses. So no matter what you have or what you're measuring, 1 mole is always equal to that many particles of that substance. So why does this even matter to us? Well, usually when we're observing stuff like a chemical reaction, that's on a macroscopic scale. So it's involving things like atoms that we can't see just by using our eyes. So what we have going on in lab is really so many atoms that you could never count them as they interact. So we use the term mole to actually put it in numbers that we can imagine when we talk about what's happening in lab. So don't get overwhelmed. A mole is just like a dozen, and as long as you can get this number, 6.02 times 10 to the 23rd, somewhere in your brain, you're going to be easy peasy for this unit. Alright, so where did this come from and what does it matter? Well, we know that 1 mole of anything is equal to Avogadro's number, 6.02 times 10 to the 23rd. However, it also goes to say something that we can't really measure stuff in moles in lab. So if you think about what types of measurements we take in lab, length, width, height, distance, mass, etc. Now, we don't ever really determine quantity in lab by measuring the number of moles. We typically measure something in using a balance in grams. So what matters to us about the history of the mole is that it came from one of the isotopes of carbon, most specifically carbon-12. So this carbon-12 atom, it just so happens that in 12 grams of that, there were exactly 6.02 times 10 to the 23rd individual carbon-12 atoms. So what's weird is that 12 grams measured out to be exactly what Avogadro's number was. So now, instead of just saying that we have this many particles or atoms of individual carbon-12, we just say that we have 1 mole of it. So a mole was derived from talking about how many carbon atoms were in 12 grams of that isotope. And the last thing on this slide that you need to recognize and become familiar with is that chemists are really lazy, and we make abbreviations for even 4-letter words. So mole is abbreviated often by MOL. So don't be confused. Mole and MOL mean the same thing. So as we've talked about, when you're measuring quantities in lab, it often has to do with the mass in grams. So remember that the mass of a carbon-12 atom is 12 grams. And we know that in 12 grams of carbon-12, there are 6.02 times 10 to the 23rd individual carbon-12 atoms, or 1 mole of atoms. So the mass in grams of 1 mole of any element is based off of this idea of carbon-12. So if you look at the periodic table at the square for carbon, atomic number 6, it has an atomic mass of 12.011. Now, those decimals come from because that really is just an average of all of the average isotopes of carbon. So the 12.011 is something that we call the atomic mass. Now, the mass in grams of 1 mole of any element, not just carbon, but any element, is equal to its atomic mass. So if I were to ask you, what is the atomic mass of carbon, you would tell me 12.011. Now, this is also called its molar mass. So while the atomic mass of carbon is 12.011, the molar mass of carbon, or the number of grams in 1 mole of carbon, is also 12.011. The units of molar mass are grams per mole, so the number of grams per 1 mole of that element. So just like we did with carbon, we can look at other chemical elements like iron, Fe, atomic number 26. If you look at the bottom of the square on the periodic table, you'll see the number 55.845, or sometimes your periodic table will round to the hundreds place and you'll have 55.85. Now, that is the number for the average atomic mass of iron isotopes. Now, what we just learned, though, was that this number is also equal to the number of grams in 1 mole of iron. So the molar mass of iron, then, is 55.85 grams per 1 mole. So, that being said, while 1 mole is 55.85 grams, 55.85 grams is also equal to 6.02 times 10 to the 23rd iron atoms, because 1 mole of anything is 6.02 times 10 to the 23rd particles. So take a few moments, look at the periodic table, and tell me what the atomic mass, the molar mass of these atoms are. Now, I kind of just gave it away, but the molar mass is numerically equivalent to the atomic mass, which we know to be the number in the bottom of the square on the periodic table. All right, so these are your answers. So the molar mass of copper is 63.55 grams per mole. The molar mass of magnesium is 24.31 grams per 1 mole. The molar mass of sodium, 22.99, and phosphorus, 30.97. If you didn't get these, I want you to pause, rewind a little bit, and see if you can understand where I'm getting these numbers. So the way that this all connects to what we've been doing in class is when we have more or less, if you will, more or less than 1 mole of some substance. So if you have more or less than 1 mole of something and you want to know its mass, well, how can you calculate it? Well, what you need to do is to just use the molar mass as a conversion factor. So the molar mass, remember, is equivalent to 1 mole of whatever element or substance it is equal to the number in grams from the periodic table of that element. So when you're doing these problems, that, for example, might be, what is the mass of 2.5 moles of Fe? All you would need to do is look up the molar mass of Fe and multiply by how many moles there are. So as you can see now in this problem, in the setup, if I start with a number in unit given, 2.5 moles of Fe, and I multiply by the molar mass of Fe, which again is just the number from the bottom of the square on the periodic table, and I multiply across the top, divide by the bottom, round to sig figs, I get 140 grams of Fe. Now, it works out that I multiply because moles of Fe needs to be in the bottom in order to cancel out. Well, on the previous slide, I wrote that molar mass of Fe, so 1 mole of Fe, is equal to 55.85 grams of Fe. So just as we did with other conversion factors, you write this as a fraction so that your previous numerator will cancel out with the denominator and you're left with an answer in the units that you want. So let's do these practice problems. Calculate the mass, so the number of grams, of each of the following. So what you'll need to do is step number 1, find the molar mass, which I'm going to abbreviate MM. Find the molar mass, and 2, multiply the number given by the molar mass. And if you're confused as to why you multiply, set it up so that you can see that the units cancel. So here are our answers to these problems rounded to sig figs. Now, if you didn't get these answers or you're confused as to how I got these answers, please send me a quick email letting me know where in the video or where in this process you're getting lost. So remember, when you're going from moles to grams, you multiply by the molar mass. So our next set of problems are going to be problems that involve going from grams to moles. So what mathematical operation do you think that's going to involve? Yep, you guessed it. We are going to divide by the molar mass. So going from grams of a substance to moles of that same substance, you divide by the molar mass. So this example problem says how many moles are in 48 grams of O2. So I set up with my number and unit given. Grams of O2 are on the top, so they need to be on the bottom over here in this part of the problem. Now, my question is, why did I write 32 grams when I look at the periodic table for oxygen, it says 16.00 in the bottom? Well, does everyone see how there is a 2 in the formula for O2? Well, that's just telling you that there's actually 2 oxygen atoms in that element. And that's because something like oxygen is found in nature as like an O2 molecule. So it's never just found as O. So the oxygen that we breathe is always O2. It always has oxygen in a pair, so as buddies. So when you do this problem, because the 2 is there, I took the 16 in the square multiplied by how many oxygen atoms there were to give me the mass of 1 mole of O2. So same way we've been solving problems before. You have the conversion factor up here. You arrange it as a fraction so that your units cancel. And you multiply across the top, divide by the bottom, round to sig figs, and you get an answer of 1.5 moles of O2. Here are some more practice problems. So this says calculate the number of moles in the following. So your steps. Number 1, find the molar mass. And step number 2, take the number given and divide by the molar mass. So for example, in letter A, we would take 88 grams of carbon divided by 12.01 grams of carbon, because that's the number I got from the periodic table. And that would give me an answer of 7.3 moles of carbon rounded to sig figs. So these are the rest of the answers for those problems. So go ahead and go back and review those, practice them, and see if you get these answers. Remember to be careful about sig figs. Well, wait. Here we've talked all about Avogadro's number, this fancy 6.02 times 10 to the 23rd. Well, why does it even matter? Well, it matters just like the periodic table does, in the sense that we can actually calculate how many atoms are in a certain number of moles of something. So just like we calculated the number of grams when we had more or less than 1 mole, you can calculate the number of atoms in more or less than 1 mole. So for example, how many atoms are in 42 moles of carbon? Well, I'm going to start with the number and unit given, which is 42 moles of carbon. Now my conversion factor, though, I'm trying to get to atoms. Well, 1 mole of carbon, or any atom, is equal to Avogadro's number, 6.02 times 10 to the 23rd, number of atoms. So I set this up so that I begin with the number and unit given, 42 moles of carbon. And now I take this conversion factor and write it as a fraction so that moles of carbon cancel. So 1 mole of carbon equals Avogadro's number. Now let's clean this up. So we multiply across the top. So now this is where it gets a little bit tricky and where you have to be really, really familiar with how your calculator works. So across the top, I would put in 6.02 times 10 to the 23rd first if I was concerned about my scientific notation. But you're going to end up taking 42 and multiplying it by 6.02 times 10 to the 23rd. And that should give you an answer. All right, so I did not put an answer. Well, let's calculate this out. 42 times 6.02 times 10 to the 23rd is equal to, this equals 2.5 times 10 to the 25th atoms of carbon. All right, so here are some more practice problems. It says calculate the number of atoms in the following. So you're given the number of moles, and all of these are going to be just multiplied by Avogadro's number, which I'm just going to abbreviate AN, which is 6.02 times 10 to the 23rd. So this number times Avogadro's number gives you your answer. All right, so here are your answers rounded to sig figs. Make sure you go and check these, confirm that you're doing things right. If you have any questions, send me an email. Lastly, we can go from moles to atoms by multiplying by Avogadro's number, but we can also go from atoms to moles by, you guessed it, dividing Avogadro's number. So in this example problem, 5.00 times 10 to the 24th atoms is how many moles? Well, you take 5.00 times 10 to the 24th divided by Avogadro's number, and you get 8.31 moles of Cr. So here's our last set of practice problems. So you'll take these numbers and divide by Avogadro's number to get your answers. And here are your answers. Everything's fantastic. If you have any questions, send me an email. You'll be doing some practice problems individually in just a moment. So please just let me know if you have any questions. Have a good day.